then the energy can be transferred to the vacuum to create more QQ bar, and then they will hydrolyze into final state hadrons. But for the lepton part, the leading contribution already large enough because more lepton pair creation will be suppressed by the electromagnetic coupling. So approximately, the ratio for the equation will be like this. You pick up the charge of the quarks, so that proportional to the fraction of the quark charge. If we have or we have a number of different flavors, then we can just sum the square of the charge fraction. So if we have the lowest U quark, we have the ratio approximately, which is 4 nines. If we adding another D or adding another S, we have the ratio which will be just like this. We have the 3 different flavor. We have the 4th flavor of the charm. We have the 5th, or we have the 6th. So we can sum the ratio to such a way it can be tested by experimental measurement. However, you will find that this number actually is different from the data, except that you allow the quark to carry a color. And for each flavor, which means each flavor, it can have 3 kinds of different color. Therefore, the cross-section ratio will be multiplied by 3. By doing this, that the ratio actually change to this sort of a number. If you have 3 flavor, then you have a ratio about 2, or 10 thirds, 11 thirds, or 5. Then if you compare with the data, and you will find that actually this R value measurement is pretty well. For the low energy part, which basically involving the 3 different flavors, the ratio almost exactly fall into the prediction of the quark model well, I would say quark model. And then when including charm and the bottom, you also have the sort of ratio. For example, including charm, by average, this kind of a phantom tells you indeed lead a charm quark. So I think this is a very convincing way to confirm you do have quark degrees of freedom. Apart from that, you also have a color. You also need a color, and this fulfill the question we encountered at the very beginning of the quark model. And of course, in 1974, that the charm quark has been discovered by these 2 gentlemen, and they got a Nobel Prize just 2 years later. And so now what we have learned about the quark degrees of freedom, or the part which involving all different interactions in the standard model, is the quarks. And we know that there are 6 different flavors, and their property can be found in this chat. And for the quark model, of course, it's just an effective sort of a phenomenology. There are certain approximations should be made. Sorry. And one specific thing to mention is that the chiral symmetry, spontaneous symmetry breaking actually will give masses to quarks. And that's why when we talk about the quark model, the quark actually is a so-called constituent quark instead of a current quark. They are massive quarks. So by doing this, and also what I mentioned, the basic assumption about the quark mass and this effective degrees of freedom, that now we have the conventional quark model describing the interaction of quarks is on average sort of potential, which is due to the background, the ground fields as an approximation, and then that the baryon can be treated as a 3 quark system, also on effective field, effective potential from the background ground interactions. So now come to the quark model. I think now we are treating just the quark system. And if we write down Hamiltonian, then basically the quark motion inside is just like the fermion, which follows the direct equation. Therefore, that with the potential for a quark interaction, we can basically describe a quark antiquark, for example, within a hadron. But keep in mind, this is a very empirical ones. I will come to the point what we have lived out or throw away, and what is a crucial assumption, which gives a reasonable description of the data. So basically, the gluon interaction is just like a potential in this kind of a diagram. Interaction.
John?
Yes.
Can I ask a very detailed question? In the first line, you have beta. I think you don't need it, don't you? I mean, this is a non-relativistic. But beta is the Dirac matrix.
That's the gamma row, gamma zero.
Zero, right?
So gamma zero is combining with this Q dagger, give you Q bar.
Q bar, right.
Yeah.
Then kinetic term is here. I think if you write in the relativistic form, alpha dot p or something.
Yeah.
Well, it's just a detail.
No, I think that you need this beta here.
Yes.
Yeah, because I'm talking about this Q bar.
Okay.
So Q bar equals. Right? Sorry, can you repeat?
You are considering this Q as a 4 components enough.
Yes. At this moment, yes.
Yeah. If that's the case, I think for the kinetic term, I think it's better to write alpha dot p.
Yes, exactly. You're right. I put this as a shorthanded sort of a way. If I do the expansion of this, of this part of the 4 component into 2 component, then I should recover this, and that will appear.
Form.
Yeah. You are right. This is a little bit short-handed. Yeah. So the potential itself, of course, I also give the color indices, in which that the lambda is a Gell-Mann matrices, which have the sort of form, and because of this, the potential itself has a feature that's a one gluon exchange potential have been introduced. So empirically, that the quark potential, or more or less, have implemented the leading perturbative sort of a scenario, even though the consequence actually is non-perturbative. So to write the QQ bar system in terms of a kind of a state, we're using this mock state to describe that, to create a quark, antiquark from vacuum, and then project the states into the momentum space. Then we have this sort of a wave function, and of course the potential itself can be right in this way, which means that only when the potential can connect these 2 quark at a certain vertices, that will contribute to the interaction, and then the color part of these 2 constituents will give indices to decide the coupling strengths between these 2 colored objects, and this can be worked out. This average value can be worked out in the color space. So for quark antiquark or quark, the representation for any 2 quark interaction belongs to either color singlet, color octet, or 3 bar or 6 representation, and by implement the representation of these QQ bar products or QQ products, we can work out these elements in the color space, and that give you the so-called the Cosmos coefficients, which decide the coupling strengths between either two quarks or quark antiquark, which belongs to certain representation during their coupling. And this is the way we construct the Hamiltonian in the end for the color part. I guess that we all have this sort of practice in the text. So as I mentioned, you have 4 representation, well, 6 representation, but one of these is a fundamental one. For each of these C coefficients or the Cosmic coefficients give you either coupling for the color signet, give you 0, these coefficients, and for the octet representation, you have a coefficient 3, or 3 bar, you have 4 thirds, or the 6th representation, you have 10 thirds. You substitute this into this V elements. These V elements I just mentioned before. This give here, and give you the potential either attractive or repulsive. And you can see for the color signet part that the contributing part actually is attractive. When you have octet, you have actually a repulsive. You have another attractive interaction, 3 bar goes to 3. That give you also attractive interaction. So we have both attractive or repulsive in such a scenario. By the way, if we don't know what's the potential between quark and antiquark, we can actually have several options. You can also have a scalar coupling, but you will find if you introduce a scalar coupling, then you will have additional sign coming in front of this potential, and that give you different scenario, which actually contradicting with the data or with the experimental observer. So that can easily eliminate the possibility that the gauge fields is a scalar field. It must be a vector fields. So I leave a question here to think about for students. So now come to some simple dynamics to organize the quark system. I just give all the symmetry organization, but to describe the spectrum energy, we need the dynamics. And a simple way to describe the dynamics for QQ bar, for example, is to write on the Hamiltonian in this sort of a relativistic way. And this is a kinetic energy, and this is a potential. And the potential has this sort of feature I just mentioned for the vector. It has a certain structure will coming out. I will come back to this part. And you can choose different coordinates to describe the motion. And the easy way, of course, is to rewrite the coordinates into internal and the center of mass motion, and then we can separate this question into a central a quantum mechanical question in a central potential. In such a case, you can see the center of mass motion just like a free particle interaction, a free particle motion, and then you have the internal one satisfy a Schrödinger equation. And to solve this central potential problem, you can also write the wave function in terms of the radial part, and also the orbital angular momentum part. And I think this is also very simple. In such a picture, the total orbital angular momentum is conserved. Therefore, the angular motion can be described by this spherical harmonic function, and the radial part can be solved depending on the form of the potential. And then by doing this, now we have the wave function containing flavor and spin and the orbital part in which that's the SU3 and the SU2 has a common symmetry of SU6, and then the orbital part belongs to the O3 symmetry. So we have the non-relativistic wave function have this sort of a symmetry. If we talk about the QQ bar, then we have the representation or symmetry for the states, for the spin can be either singlet or triplet, or the flavor can be either singlet or octet. And then the spin flavor can form a spin flavor singlet or 35 multiplates. All this give us the quark model conventional spectrum for QQ bar. I think that my speed is, I should speed up a little bit. So I already give this sort of arrangement before. I skip this. Now for if we talk about the overall wave function, then we can always organize the spin and orbital angular momentum to form the total angular momentum by momentum coupling, and the flavor wave function and the color wave function can be combined to give a total wave function. So that's basically is the picture what we have learned about non-relativistic QCD, non-relativistic quark model, and the system must be anti-symmetrized because they are fermion system. If we write out the eigenstates of a spin flavor for QQ bar system, you can see that, for example, for either Schultz-Skinner K or vector K star, we have this sort of a combination to keep that's the symmetry, keep them to be the eigenstates of flavor symmetry. As we know, that Schultz-Skinner has a positive C parity for the neutral one, for the neutral state. Therefore, when the quark becomes to anti-quark, then we keep this sort of a sign to be unchanged. So we choose the plus sign. But for the vector, the neutral vector, like a rho 0 or omega or phi, that give you the C parity negative. Therefore, we keep this convention that when we do the charge conjugation transformation, that give you a sign for the flavor wave function. So we set up all these states in the as the flavor eigenstates. Well, this is a brief history since the quark model discovered, and then later we recognize that by deep inelastic scattering, that the quark itself is not just the constituents. There are actually many quarks inside the hadron, depending on the energy scale we're talking about. And then the strong interaction will describe one of the most important part in the standard model for the strong interaction, and the Young-Mills gauge theory has been implemented, but it's until later that the full field of the QCD part has been achieved in 1970s. Come to the baryon part, we can also do the similar sort of thing. When we combine three quarks together, we have the color decomposition, in which that for hadron, it's only pick up the color singlet. And for the spin flavor, that we still have the SU6 as a combined symmetry for spin and flavor. And for three quark, that is spin symmetry can form either symmetric representation for, or a mixture symmetry of the doublets. And for the flavor, we also have a symmetric, anti-symmetric, and the combined symmetry. I use the superscripts S and A denoting the symmetric or anti-symmetric by interchange any two of the particles. I use the lambda and the rho to describe the symmetry by interchange the first two quarks. Therefore, I can do the overall anti-symmetrization of the wave function. So this convention, I will come back later, and this is usually what we applied. So the spin flavor, the total decomposition will give this sort of a representation, which means for each quantum number, we can have so many states coming out as the multiplies of either spin and flavor and involving orbital angular momentum. In total, we can use the representation of the SU6 and also SU3 flavor and the spin, and then the total main quantum number, total orbital angular momentum, and the total spin to describe a baryon wave function in this sort of way. If you have questions, please just stop me. We now have set up so many baryons in experiment, and if you look at the non-strange part, which can be resonance states of either UDS, UD, or well, composed either U and with U and D quarks, the so-called nucleon resonances. We've already seen tens of them, and we have observed these states in different decay channel. And the star means their status. 4-star means they are very well established. 3-star is well established. 2-star means that their status is not so determined. 1-star is just some very brief signal have been seen in single channel. So too many states means that the internal structure or dynamics somehow is very complicated. For the strange part, UDS, the lambda spectrum, is also complicated. We have seen also more than 10 states. Some of these are well established, and some of those are not so well established. So there are so many things to be learned about this Hadron spectrum. I skip all the others because you can easily check that in the literature. I come to the organization of the wave function a little bit. I just give you the symmetry sort of arrangement, but when we come to the detailed expression for the wave function, we have to be to go to a little bit detail. As I mentioned, I use the superscripts or subscripts to describe the symmetry by interchange any two of the quarks or the first two quarks, because this interchange makes the wave function to be a representation of this permutation group. For example, the P3 or the P12 means that by interchange the first two quarks or two particles that they have the eigenstates for lambda type is 1, therefore it's symmetric. For the rho type, when you interchange the first two particles, there will be a sign coming out. Therefore, the wave function is anti-symmetric. But if you interchange 1,3 or 2,3, you will find that you don't have the eigenvalue coming out, because the operation of this operator on any one of the states will change the states to be a linear combination of these two representations. Therefore, this is not have eigenfunction, and these two things are not eigenvalues. So we don't interchange 1,3 or 2,3 for these two representation, but we keep that rho and lambda symmetry to construct the symmetry we need. If we look at the spin wave function, that the total spin 3/2 will have for example, a symmetric sort of states, which is the eigenstates of the spin projection. If we have the rho type, which means that the 3 quarks must be organized in such a way their total spin must be 1/2. And when you interchange the first two quarks, the spin their assign will arise from the wave function. And for the lambda, the way we organize it will make it to have a symmetric structure when you interchange the first two quarks. And so we can construct actually the spin and the flavor a sort of a similar way by write the wave function in terms of the 3-dimension permutation group symmetry or 3-dimension permutation group representation. So the wave function actually are eigenstates of this three-dimension permutation group. For the antisymmetric one, by interchange any two of the quarks, that will give a sign coming out, which can be easily checked. So we can construct the octet, lambda type octet or row type octet. For the proton neutron, you can see the lambda type when you interchange the first two, that this is symmetric. And for the neutron, similarly, you have a symmetric wave function. And for the row type, the proton wave function becomes to be antisymmetric flavor, and the neutron also antisymmetric. So we're going to use all the wave function to construct a total wave function. I skip this because I have mentioned. So the total wave function for the SU6, which is a part of the SU3 coupled to the SU2, as I mentioned, you have this 56 multiplates or 70 multiplates or 20 multiplates, which is antisymmetric. And then we can use a spin flavor wave function we just constructed to construct a symmetry in this sort of a language. For example, for the symmetric wave function, when you interchange any two of the quarks, you have a symmetric wave function that give you this sort of a combination. You have the row type coupled to row type spin, row type flavor coupled to, oh, this should be 5, sorry. Row type spin and flavor that give you symmetric. Therefore, this is total symmetric wave function. And you can construct the mixtured symmetry, the 70 plates, or totally anti-symmetric 20 plates. By the way, at this moment, there's no any experiment evidence for the 20 plates in experiment. This has been, to my knowledge, this has been studied or has not been investigated in detail in any experiment. Or in theory, there are very few study of the anti-multiplates of the 20 states. So with the spin flavor wave function ready, I think the rest thing for us to do is to have the dynamics implemented to describe the energy spectrum, which means we must have a Hamiltonian, and then we must solve the Hamiltonian to get the energy level and also wave functions, as what we have done in quantum mechanics. So the usual way to write down the Hamiltonian, of course, which contains the static mass, kinetic energy, or the potential, including the confinement potential and the hyperfine splitting part, which is a spin-dependent force. For the confinement part, generally the way to have this is the Cornell potential type of a form, which contains the zeroth energy, which is a constant, or linear potential, and also Coulomb type sort of potential, which coming from the spin-independent part of the 1 Coulomb exchange. And for the hyperfine splitting part, which contains the spin orbital and the spin-spin interactions can be absorbed into this part. Concentrate on the light and light hadron sector, and also the Iskar-Karl model. They propose a more analytical way to solve this Schrödinger equation. They propose that this confinement potential can be mimic or can be sort of simulated by such a harmonic oscillator plus unharmonic part. And by doing this and minimize this Uij, that you can have actually a harmonic oscillator potential. Treating this U as a perturbation, this harmonic oscillator potential can be analytically solved. Therefore, you can see in the literature that Iskar-Karl model give an explicit form for the wave function when that this Schrödinger equation is solved. And then later, by introducing this U, which is spin dependent, they can introduce state mixing. But at this moment, I would like to say that even using the harmonic oscillate potential, this solution turns to be quite successful. But if you look at the confinement potential, this expression with this one, you will possibly have the person who say that when R is small, this becomes to be very, very important. When R goes to large, this becomes very important. Why this sort of behavior can be simulated by this? I think this is because of the QCD strong interaction is scale dependent, and this sort of scale determined by K is more or less at the energy of the constituent degrees of freedom. Therefore, that part of a potential indeed have a kind of a similar behavior, and that's why the energy level can be reproduced by this harmonic oscillator.
Yeah.
Yes.
I got a chat message from Zhang Wang. Maybe he or she can ask a question. No, is that all right?
Oh.
Can you see the chat window? Can you open the chat window?
Yes. My question is that why the constant potential should be absorbed into the redefinition of the constituent mass, quark mass.
That's already done. Yes. So
I wonder whether it is necessary to have a constant C in the potential.
That's depending on whether you fix the constituent mass or not. If you fix that, and that C can still be there. Yeah.
Mm-hmm.
So, for example, if we fix more or less the constituent quark mass, and then by describing physics data, you can determine K. Right? This is one way you solve this problem. The other way is that you try to extract the potential based on this expression, and then describe that potential using this. Then you will be able to say by adjusting the effective mass to which extent you can best describe this part. Yeah.
Okay. Okay. Thank you.
Okay. So come to to solve this equation. I think this is also very standard. You can choose a so-called Jacobi coordinate, or you can just solve a single particle with Hamilton single particle Schrödinger equation. But of course, using harmonic oscillator, this will help a lot to separate the internal degrees of freedom. That's one thing. The other thing is that you can indeed benefit from the symmetry. By defining the Jacobi coordinate, you can see that the wave function itself also belongs to the representation of the three-dimension permutation group symmetry. So you can now again organize the wave function, the spatial wave function, in terms of the permutation group symmetry. So this is I gave the different state in terms of the symmetry of the permutation group, which means that by interchange the first two quarks, then you actually interchange the coordinate or interchange the momentum, and that will possibly bring sign to the wave function, and you can define the symmetry. So in principle, we have the spatial part also organized in terms of the permutation group. So coming to constructing the wave function, you can see for the ground state that this coefficient function is just a constant. The wave function itself, the quark motion inside the hadron, is a Gaussian type of a distribution, and this is corresponding to the ground state baryon. And then that the symmetric total spatial wave function means that the spin flavor combined together should be also symmetric. And for the first radio excitation, first orbital excitation, you can also write down the wave function in such a way, and you can see this is a coordinate. This rho and the lambda also belongs to the symmetry, or belongs to the repetition of the permutation symmetry group. For the radio excited states, in which that the L equals node, but the quantum number is 2, and you can write down this combination. You can construct a symmetric one, or this mixed symmetry. For the orbital angular momentum L equals 2, you can construct more complicated wave functions. Combining together, the nucleon wave function becomes to be as simple as this one, in which the spin flavor itself symmetric, and the total the spatial wave function is ground state symmetric, and the delta, which is belongs to the decouplate, have the symmetric spin and the flavor, and also symmetric spatial wave function. Well, similarly, you can have all the other combinations for any quark model multiplays, which can be compared or can be assigned to experimental data. And I think this, for example, the first orbital excitation, you have the 70 multiplays, but you have the spin and the flavor, different combination of spin flavor, which means that you would predict based on quark model, like this sort of doublets, and indeed they are observed in experiment. I will mention this later because this is also confirmed by the lattice QCD calculation. For other states, I just give the wave functions in detail here. If you want, I mean, if the students are interested in this, they can just check and use. I would like to mention the 20 plates. Oh, this L equals 2. This looks a little bit more complicated, but still, you have the total, all the wave functions following the rule that they are interchange the quarks that keeps to have the spin flavor and the spatial symmetric. Yeah, I'd like to mention these multiplays. This is the anti-symmetric multiplays for the baryon, which means that you really can't have these states for the ground state. Just imagine that the spin flavor anti-symmetric. If it's ground state, then the ground state spatial part is symmetric, and the color is anti-symmetric. So combined together, you have a symmetric part of a total wave function, which is violating the Fermi statistics. So the 20 plates must come from the excitation states when you have the anti-symmetric spatial wave function combined together to give you a symmetric spin flavor and spatial part. So, however, so far there's no any experimental evidence for the existence of these states, and I think this is an interesting question for the baryon spectroscopy, to which extent we can believe or can justify the existence of these degrees of freedom. I think this is still an open question. How much time I have?
Well, thanks for listening until 4
I can have
you can do a bit more.
Okay, sure. So I supposed to actually I skipped the break, right? I forgot the break.
It's up to you.
Can because I noticed that I supposed to stop at 11. I mean 12 of your time.
If you want to stop, maybe we can take a short break now.
I'm okay, or I can also just continue and then leave 5 minutes for questions or discussions, 5 or 10 minutes. Is that all right?
Yeah, that would be nice. Yes.
Okay. So I mean, even though that the non-touristic quark model provide a very simple and a very easy handle sort of a scenario describing the hadron spectroscopy, and it turns to be successful. But there are certain sort of issues or questions also arising which cannot be explained in such a simple picture. One of the very famous questions is about the energy sort of a reversing of energy line between the first orbit excitation and the first radio excitation. You can see that in this sort of harmonic oscillator basis, that the quantum number for the first radio excitation requires the main quantum number to be 1, to be 2. Therefore, the energy of the first orbital excitation is supposed to be higher than the first orbital excitation. But in experiment, we only see the first orbital excitation is 1/2 minor states coming out around 1.5 GeV. But we have indeed 1/2 plus states, this so-called P11, which is just about 1.4 GeV. So this cannot be explained at all in this in this harmonic oscillator basis, and this has raised many questions. And this may not be surprising because, as I mentioned, at the so far the harmonic oscillator solution is taking such a scheme that the spin-dependent part has been minimized. This spin splitting part has been possibly underestimated. You may argue to see why that the minimization of the splitting of spin-dependent part can still fit in somewhere of the excited states. I think this is related to the question that Chen just asked. The mass of the constituent quarks will more or less affect the energy splitting. You take into account the width which has been observed for all these states. The minimization of this spin-dependent part seems to be justified. But when you look at the more important mechanism will have an impact, like the mass splitting or mass reversing between S11 and P11, I think this tells us that this non-twistic or harmonic oscillate solution must be breakdown. But still, you can introduce the spin-dependent force, which means that the energy level will be split. One famous example is that for the ground state 3/2 and 1/2 states, their mass can be split by this kind of a spin-dependent force. For example, if you have 2 of the quarks to always have a spin 1, and 1 of the 2 have a spin 0, which corresponds to nucleon and also to delta resonances, and you can see the splitting actually is sizable. You can introduce this operator to work out these elements which contribute to the energy, and you find that it contributed to quite a large kind of value because this is proportional to the alpha h to the power of 3, and alpha h is the harmonic oscillator strength, which is about 400 or 500 MeV, and you work out the energy splitting actually is quite large. So this mass splitting by introducing the angular momentum dependent or spin dependent force can give a leading order correction to the masses even for the ground state. For example, for the nucleon, for the delta, for the sigma or lambda cascade omega, it will introduce the mass splitting to a certain order, taking into account the mass difference between UD quark and the S quark. You can have additional sort of a term coming out. This is you just sandwich the operator for the spin dependent force into the wave function. You can work out this part. And another consequence from the spin-dependent force is that it will introduce transition between different states of the SU6 cross O3, which means that as long as you take into account the spin-dependent force, that the state mixing is inevitable. For example, even for the nucleon, apart from the ground state 56 representation, you can have the radio excited states or the second orbital excitation states can mix with the nucleon. So the nucleon itself becomes to be much more complicated than the simple harmonic oscillator strings, and this can be fitted by data as long as the Hamiltonian include the spin-dependent part. Yes.
And that's equation 44. Those coefficients are determined, as you say, from the data or by diagonalizing some model Hamiltonian. Can you just remind? I think this has been.
Yes. They are determined by fitting the data.
Fitting the data.
Yeah, fitting the data, and then diagonalize the eigenstate to be to diagonalize the mixture state to get the energy to match the data. Therefore, the state will have a mixture.
So certainly not only for the ground state nucleon, but other variants.
Yes, for the excited states as well. Not just for nucleon. This is a bunch of all the states for all the octet or all the for the all the decoupled and even for some of these excited states, because you can see this involving the first orbital excitation and the second orbital excitation.
Yes.
So if I have the wave function, a leading order of the harmonic oscillator to couple via the spin-dependent force to each other, this will contribute to the expansion of the state of the physical state. And then by diagonalize this state as the eigenstates of the Hamiltonian, then you can have the energy level to determine some of these parameters, like this alpha S will have a energy dependent part in coupling in the expression.
Okay, thank you.
Yep. So, right. So I think because this part is more depending on the static property. So I think I should finish this before the break. And this simple picture tells us that the baryons or meson actually has an internal structure made of composed of quarks, constant quarks, and the quark has a charge, has mass, has spin. Therefore, it tells us that the nucleon must have a magnetic moment. This is, of course, turns out to be a very important prediction or sort of a success of a quark model. Just imagine that we have a neutron which is charge neutral. If neutron is an elementary particle, it does not supposed to have a magnetic moment at all. However, that we observe that the neutron has a magnetic moment, which of course is an anomalous magnetic moment. The reason is because that the quark distribution inside of the nucleon will need to the dipole moment to be non-zero. Therefore, if you calculate that the magnetic moment of the hadron, it must be the sum of the constituents, their contribution to the magnetic moment, or if there's an orbital angular momentum, that will also contribute to the hadron's magnetic moment. So we can check for the ground state, which made of the quarks, that their magnetic moment will contribute to the hadron magnetic moment, and in such a way we can write down the hadron magnetic moment can be matched to the quark level average value from the quarks. And by taking a certain projection of the total spin, we can work out these elements, this average, and we can check whether this picture works or not. And by doing this, to be a little bit pedagogic, you can just substitute it into the wave function and neglect the spatial part because the initial and the final state that will be normalized. So only spin flavor will contribute to the operator, to this operator, and you substitute the magnetic moment defined for the quark, and also the spin projection to certain z direction, and you pick up for each quark their magnetic moment and also spin projection to give you the total magnetic moment to certain spin projection. So that gives you the sum of all this, and you can find that give you this sort of number, which is non-trivial. Interesting result, of course, will be from the neutron. And in the neutron, you will find that we have a 2D and one U quark, and this is very similar to each other. But because of D quark carries a negative 1/3 of the charge, and this number actually becomes non-zero, and this gives you actually a ratio between proton and neutron, which is a minus 2/3. No, 3/2. Sorry, minus 3/2 of the ratio, which is very well fitting a number which we measured the experiment, which is a negative 1.79, nearly negative 3/2. If you look at the other states, you can also have a similar sort of relation, which can be justified or can be compared with the data, and most of them actually pretty well consistent with the data. Of course, we don't have a way to directly measure the magnetic moment of all these states, but we can indirectly measure the contribution from this sort of a number and extract this from experiment data. Okay, I think oh, it's great. I think that I can just stop with a very brief summary. I think that by demonstrating this very simple sort of a phenomenology, naturalistic quark model, the main point is that the color degrees of freedom, of course, is crucial, help us to recognize the more fundamental or deeper dynamics within the hadron or intrinsic property of hadron. We know the existence of quarks. I hope that I convince you quarks are real objects, and certain observers tells us this effective degrees of freedom are pretty well, and the constant quarks indeed tackle some very essential property of the strong interaction in the non-perturbative regime. And I think this effective degrees of freedom involving massive quark, which carries the quantum number of the current quark, but turns to be massive, is a certain degrees of freedom. And on the other hand, the lattice QCD can tell us whether this phenomenology makes sense or not. I will have a slide later to show that this degrees of freedom indeed is successful. So before I come to a new part, I think I should stop here, and I'm happy to have questions at this moment.
Thank you very much. First of all, thank you.
Yeah, thanks. Yeah.
John, can I have a question to you?
Yes, please.
A very interesting talk, and so you just have in a review talk about so far the constant quark model for the especially a nucleon case. But so, can you tell me that the historical background for the heavy baryon system? Because
yes.
And in the textbook, always they say that about some baryon on lighter baryon system within the framework of the constant quark model. But so that when they start to study about the heavy baryon system within the framework of the constant quark model.
Yes. Yeah. Well, actually, I'm going to come to the heavy quark in later lectures.
Ah, okay.
Yes, because that's indeed, as you mentioned, this is a focus of the interesting topics related to these exotic candidates.
I see. Okay, I
observed
should
in
hurry up.
experiment.
Okay, I will wait
Yes.
for the facts.
Yeah. Okay. So I will come to this in later.
Okay.
Any questions from audience? Yes, please.
Professor Clark, so
Oh, well, I think they.
actually, I have kind of a naive question. So we know initially we have this back model. So basically you can solve the wave function as one body. So now you have to, you are using also some kind of phenomenological model, but you have to solve the wave function of three-body system. That is much more complicated, right?
Yes.
So then you, I mean, you are basically still kind of phenomenological, and the I mean the interaction, of course, it derived from something. But what's the advantage comparing with traditional back model or potential model?
Yes. Well, this is a very good question, I would say. I give you an example why that sometimes this three-body system, this sort of a three-body effective degrees of freedom makes sense. We know back model actually solving one body within a bag, one body motion within a bag. Therefore, the interaction is much more like a local interaction. Everything has been absorbed into a potential. But dealing with the three-body system, and the three-body in transition, for example, you have actually non-local interaction introduced. So we do have sort of case that you need this sort of a effective degrees of freedom coming out to manifest themselves. One recent famous example is in many meson weak decay or hadron weak decays, the pole term is important. For example, in B decay, in B meson decay into two-body final states, you constantly see that the I take another example because B decay is a two-body problem. I take another example. Baryon decay, lambda C, or lambda C, for example. This is one of my recent interest. Lambda C decay into lambda pi or sigma pi. In this case, that's if we can, you see many calculation based on perturbative QCD factorization, because the pion emission in the final states, the coupling strengths can be absorbed into local coupling, which is factorizable, for example. But you see large deviation in experiment. For example, lambda C go to lambda pi is okay. You can emit a pion, but lambda C go to sigma pi, you can't directly emit a pion. You only have the non-factorizable part coming out. And in that case, you have the pole term coming out, which is directly related to three-body degrees of freedom. But you can also use the back model calculation, but the back model cannot distinguish how the pion is emitted. You don't have a pole. You can, I mean, you can, the pole contribution in the back model is not obviously necessary. In that case, you can absorb everything into the weak transition operator immediately related to the final pion emission. So we do have certain cases to show that the non-local interaction arising from three-body effective degrees of freedom are important.
I see. Thank you very much.
Yeah, thanks.
Any other questions?
Excuse me, question.
Yes.
Hello. About the radial excitations in the light baryons, I mean in the nucleon sector.
Yes.
I mean, it seems that the ordering is reversed between
Yes.
the radial excitation and negative parity state. But actually in heavy baryons, I think the situation is in the opposite directions. I mean, it seems to have like a normal ordering. Well, what do you think about this situation?
Yeah, I think, well, thanks for the question. As I know that our colleagues, which is sitting in the audience, like Okasan and Hosaka-san, they both have a contribution to this sort of question. But I think that the reason in the light sector, the mass ordering is mainly because of the Kara symmetry breaking effects. There is a lattice simulation by the Kentucky group. They have shown that the when you extrapolate the state goes to Kara symmetry limit, that the ordering, the mass ordering, energy ordering will reverse. If you stay at the relatively higher pion mass, you still see the normal ordering, that the P11 is heavier than S11. But when you go to a lower mass, pion mass limit, you start to see this sort of the reversing. And they claim this is a manifestation of the Kara symmetry breaking in the light sector. So that's one of the possibility. The other possibility, phenomenologically, people proposed is that if you look at the orbital excitation in this case, the orbital excitation generally has a mass splitting about 500 MeV, that sort of order. So, which means if you excite a nucleon to pay a price of 500 MeV, it's maybe more easier to create a QQ bar, a pion, for example, a negative parity of a QQ bar from the vacuum, instead of the 0 plus sort of a QQ bar pair. So this is 3p0 creation compared to this sort of a Kara recreation of QQ bar, maybe that's not well, maybe more easier. So in that sort of case, that you pay a price for the orbital excitation, maybe compared to the easiness of just radio excited states, maybe are different. But this is very phenomenological, I guess.
Jian, can I make a comment on that?
Yes, please.
First of all, the person who asked this question is Jafar, who is in our group.
Yes.
And he's also very much interested in this Roper resonance. He's looking at this problem right now. Anyway, and the comment you made about the lattice calculation seems to be still kind of under debate. And if chiral extrapolation to the lighter pion mass doesn't seem to be quite convincing. And okay, I think if Ishii-san is listening to this lecture, and we have Professor Ishii-san in RCNP, and who is doing a kind of, he's an expert in lattice calculations. He actually right now doing the Hadron group calculations. But he will look at the Roper excitations again. And I hope that he will tell us a bit more definite, conclusive things. But it's still, it's kind of questions that we have to be able to answer this Roper resonance. So okay. I think we keep in touch in discussing this Roper states.
Yeah, I agree. This is still an open question. Yeah. As I know that the results from the Kentucky group, right. It took them quite a long time to have their work published.
Yes.
And there are several. I mean, several times there were very hot discussion on conferences.
Yes.
Yeah.
I hope that we can also add some more discussions on this local resonance. Yeah.
Sure, yeah. Oh, one thing I'd like to mention is that there are data from JLab experiment to look at the Q-square dependence of the nucleon form factor, transition form factor, and the Roper has the transition form factor for Roper indicating a large contribution from the so-called pion cloud, which means, as I just mentioned, which means that when you excite a nucleon radially, pay no price to the orbital angular momentum excitation, it's easier to have the pion pair to be created than the one single orbital excitation. I think that's the main sort of a point. You can have a two pion have a mass about 300 MeV, but one orbital excitation have an energy of 500 MeV. So to create a 2 pion staying in a 0 plus does not contribute to any orbital angular momentum or spin. That can easily excite a nucleon to a radio excited state for the light sector. Yes. So this phenomenologically can be compared with the JLab data. I'm not so sure whether you have been aware of these results or not.
I know what they yes, and there is a nice review by Craig Roberts and
and also Volker Berker, yeah.
Yes. Okay. So any other questions from audience, from the Zoom? If you have, please do not hesitate.
Yes, excuse me, may I ask a question?
Yes, please.
My question is about the hyperfine.
One. Okay. Yes,
yeah.
Please.
Yeah. My question is about the hyperfine splitting potential. Why the tensor force is proportional to the 1 over the r to the third? The hyperfine splitting potential.
Where I put it?
Yes.
No, not this, not here. Oh no. Here. Where is it? Here, this one.
Yes.
Yep.
Yes,
so,
here.
Chen, yeah, you have this. You have here.
Yeah,
you
this
have
is the tensor force.
Yes.
Where is the prefactor 1 over r to the third power?
Oh, well, I think this is just from the operator. You have the orbital part, orbital and spin coupling. From the Hamiltonian, you already have the 1 over r square when you write down the orbital angular momentum. Okay. So I mean, in the central frame, in the spherical frame. So that's from the operator itself and from the Hamiltonian itself will already give you that sort of a dimension.
Okay. Yes. Even compared to the first term, it should be the inverse to the r to the third power because the delta had function. Yes.
Can I make a comment on that? I think can I make a comment?
Yes, please. Yeah.
The starting point is a 1 over r type potential, which is the one gluon things. But the tensor force contains the two derivatives, sigma from the sigma dot nabla. So you apply the sigma dot nabla to the twice to this 1 over r. That's the origin of the 1 over r squared. That's the same calculations when you compute the dipole interaction in electrostatics.
Yeah.
Is that okay?
Yeah. Thank you very much.
Yeah, thanks for the comments. It's more explicit.
Yeah. Okay, so any other questions? Is that all right? Okay, so I think then shall we stop the morning session? Jan, is that okay?
Yeah, thank you very much. Yeah.
Okay.
Yeah, thanks. So I will see you later.
Yes. By the way, I forgot to tell you that is it okay to make a record? Actually, we have already
To make what?
Yeah, I did. I'm doing that now.
Yeah,
If you don't
recording.
mind, recording.
Oh, that's no problem. Yes, of course.
Yeah, thank you very much.
Yeah.
All right, then I think the afternoon session will start from
2
o'clock
in Japanese.
time. So maybe
1 o'clock for me. Yeah.
Yes.
from your side. So I think that there are many people from the China. So 1 o'clock afternoon session.
In Chinese time.
Yeah, in China time.
Yeah.
Japan time 1 o'clock. Okay.
Okay, see you later.
Okay. See you later.
Okay, see you later. John, thank you very much.
Bye.
Bye. Bye for the moment.
Okay, it's a lunch time.
僕弁当っつって持ってきましたよ。
1時からって何があるんだっけ、保坂さん。
1時から特にないです。
なんもないっすよ。
あ、僕はちょっと。
あんの？
いや、わかんない。ないと思う。
じゃあ、shall we have a lunch in my room if you want?
今日はないです、僕は。
And so I
今
will
日はないんですよね。
already I made the lunch box by myself.
Which
なんかみんなまだね。
No.
岡さん、
はい。
こんなところで、まだみんな入ってるところですけど、特にないです、僕は。どうしましょう。
次は金曜日よね。
はい。
Please bring.
いや、いいです。次は金曜日だったらいいんですか。
ああ、次のレクチャー、今日の午後と、それから、
今日の午後何なんだっけ。
今日の午後2時から、2回目のレクチャーです。あ、違う。そう。今日の午後2時からレクチャー2です。
今日の午後、ごめん、何があるんだったっけ。分かってないね。
いや、彼の2番目のレクチャー、2回目のレクチャー。
彼の 2番目のレクチャーって今日の午後あるんだっけ。あれあ、本当。
でそこで一応予定ではエレマグの性質とストロングディケイ。
ごめん。今日の午後は僕は予定を入れてしまったんだな。あ、そうですか。何時からって言いましたっけ。
2時から、まあ一応90分の予定です。
あ、わかりました。了解です。はい。どうもありがとう。
もし、で、それついでに金曜日は10時半からです、また。
はい、わかりました。どうも。すいません。ピントがボケていました。今日午後あるのを知らなかった。はい、すいません。
個別に確認をしてます。それじゃあどうもありがとうございました。とりあえず書きます。I will quit for the moment. Okay? 一旦終了しとくのがいい。